morning, everyone. My name is Laila Koubaa, and I'm a PhD researcher in architecture from Carthage University. Today, I'm going to present my research about generative design for sustainable urban morphology. And this research was conducted by me, Laila Koubaa, and Professor Abdelkader Ben Sassi. The current context of urban densification and the energy transition of the building, it's obvious to integrate solar energy into architectural and urban design. Energy saving in architecture has been a major challenge since the oil crisis of the 70s. And optimizing the morphology of buildings is a lever to reduce energy consumption, in particular by ensuring solar access to neighboring buildings. The solar right appeared in the late 70s through the concept of the solar envelope described by Ralph Knowles. This morphological concept guarantees this right by allowing solar access to a building without shading its neighbors at specific times. The cut-off time and the shadow fences are the two constraints of the morphological definition of the solar envelope. Shadows are script within a virtual spatial boundary called the shadow fence, which defines the shadow projection boundary of the massing. And the cut-off time defines the period for which solar access is desirable. It is determined essentially according to the period of useful insolation or solar energy collection. Most cut-off time determination studies focus on desirable solar access in winter. However, this period corresponds to the overheating hours in summer. Hence the question, what will be the optimal solar access period in winter and summer, and not only during the winter period? We propose in this research to maximize the direct solar radiation received in winter and to minimize the direct solar radiation received in summer. We define for given place the shading cut-off time by calculating the sum of the direct solar radiation in winter and the sum of them in summer from sunrise to sunset on different orientations of facades. We refer to the Pareto principle to define the retained time period, and we propose that the time period retained in winter be around 20% of the hours of the day, which corresponds at least at 80% of the total radiation. We proposed the energy balance factor denoted Q, which characterizes the ratio of these two radiations and qualifies the relationship of the direct solar radiation received in winter and summer. And we consider a range of shading cut-off time satisfying the previous condition. And we show the shading cut-off time which has a maximum coefficient corresponding to a high solar radiation rate in winter and a low one in summer. We present an application example on an urban block of 3 plots A, B, and C located in Lake of Tunis, and we propose a workflow based on a Revit environment. We use Dynamo for parametric algorithm that will be involved on generative design by refinery. And the selected solution is exported to Revit for solar analysis. We have developed an algorithm on Dynamo for the generation of the solar envelope by shading exchange. The program makes it possible to detect the boundaries of the parcel imported from Revit, establish the layout of the building, and generate the solar envelopes for each variation of the shading cut-off time. It also calculates the FAR and the FSI from the variation of the shading cut-off time for each parcel of the block. The inputs are the location of the site start time cursor T1 and end time cursor T2 of the shading cut-off time interval. The outputs are the FAR and the FSI urban density indices and the shading cut-off time duration. These inputs are represented by a diagram axis and 3D solutions are generated. The generative design makes it possible to generate a digital model of different density solution by varying the solar access duration. Generative design can offer advantages to traditional urban planning process, given its capability to manage complexity by optimizing heterogeneous pre-selected criteria. The aim of this research, of this approach is to exploit the solar morphological potential of each plot. The position, shape, and size of the plot impact the far and the solar axis duration. The generative design makes it possible to study different urban density solution by varying the shading cutoff time, and the cross product on generative design makes it possible to obtain multiple variants for each plot. The multidimensional representation below allows us to see the implications for all the variables considered. Once the optimal solution has been determined, we export the results back into Revit environment to complete the BIM modeling for solar study. We evaluate the solar energy for the generated solar envelopes, and we calculate the solar energy received on them at the shadow cutoff time for winter and summer. The seasonal energy balance between overexposure in summer and access to the sun in winter allows reaching high energy and environmental efficiency of the buildings. The comparison of the result obtained with the current urban regulation of Tunis shows a clear improvement by using this model. We notice that this approach improves the maximum height indicated by the urban regulation. It can increase until 30 meter compared to 70 meter as indicated by the actual urban regulation. And the model allows a higher building guaranteeing solar access. We examined the results by two studies where the goals are maximize far and maximize the solar access duration. The virtual environment created allows exploring urban morphologies resilient both to urban densification and better use of the context resources. We propose a method for designing buildings and neighborhood in a virtual environment. The latter acts upstream of the design process and can be extended to different phases of the building life cycle, detailed the design, constructions, and use. The study of maximum far and the duration of solar access makes it possible to obtain the best solution for each plot, and the multi-objective approach will be necessary in this case. We have proposed a new model on two topical axes. The first axis of digital transition. The model promises a revolution in the framework of urban regulation by moving from fixed specifications to a generator that verifies compliance with solar access on the scale of the urban block. That will replace urban regulation via digital model. The integration of BIM makes the model accessible for transcription into architectural form. It's the first operational application. In addition, a second new is that of the energy transition. The model allows the designers to anticipate the energy balance from the first phases of design. The generators present a directory of shapes respecting solar access and desirable solar gain according to the climatic region. The proposed approach makes it possible to guarantee better use of solar research on the building envelope. Here we have calculated the solar research a posteriori. However, we can consider this variable as a parameter to select the optimal urban morphology. We propose a perspective to refine the determination of the shading cutoff time according to the use and energy consumption. This being to adjust the morphology of the optimal solar envelope to the actual needs of the buildings. For example, assuming the installation of energy capture devices, if the shading cutoff time interval makes it possible to reach energy values that exceed the needs of the construction, the shading cutoff time could be reduced in favor of the neighbor. And I would like to thank ASCAAD committee for this opportunity, and we're still available for any question and constructive comments. Thank you.